All right, let's talk about the big leap. The one that separates a cool project blinking on your desk from a real-world product that ships to thousands of people. We're diving into system integration and deployment. This is where the real magic and the real challenges begin.
So you've been grinding away, right? Weeks, maybe months, getting your firmware just perfect. It runs like a dream on your dev board. But now what? How do you actually get that code onto 1,000 other boards, reliably, safely, and without losing your mind? Well, that's exactly what we're going to unpack. Here's our roadmap. First, we'll talk about integration, which is like assembling a complex puzzle. Then deployment, getting the code onto the hardware. After that, we'll get into what happens after launch, updates, and security. And we'll wrap it all up with automation, the secret sauce for a professional workflow.
Okay, first up, integration. And look, this is way more than just hitting compile on all your files. It's the delicate art of making every single part of your system, from the hardware drivers to the cloud connection, actually play nicely together.
The key word to zoom in on here is constraints. It's not enough that your different software modules just kind of work together. In the embedded world, they have to work within super tight limits. Are you using too much memory? Is your response time fast enough? Are you absolutely draining the battery? That's the real challenge of integration.
So how do you actually do this without it becoming a total nightmare? You follow a process, a methodology. You start small, test each little piece by itself. Then you test how they talk to each other. You build up, piece by piece, testing performance along the way. And finally, you do the fun part, stress testing, where you basically try to break it on purpose just to find its limits.
All right, once everything is playing together nicely and passing all your tests, it's time. This is the moment of truth. Deployment. We're taking that perfected code and flashing it onto the hardware for good.
And how you do this totally depends on what you're working with. For something like a Raspberry Pi, it's more like setting up a tiny computer. You're often deploying a whole operating system image. But for microcontrollers like an ESP32 or an STM32, you're getting way closer to the metal, using specialized tools to burn your code directly onto the chip.
Let's break that down. With a Pi, a huge step is just making sure your app starts up automatically when the device boots. For an ESP32, you're probably going to be in the command line using a tool like ESPTool to push your binary. And for an STM32, you're often bringing out the heavy-duty hardware, like an ST-Link programmer, to get the job done. Okay, so your device is deployed. Awesome. Time to kick back and relax, right? Not even close, because now the real fun begins. What happens when you find a bug, or you want to add a killer new feature? Your devices are out in the wild now. This is where updates come in.
And the unsung hero of the entire update process is the bootloader. Think of it as a tiny, bulletproof little program that's the very first thing to run when the device powers on. It's the bouncer at the door. It checks the main application's ID, and if you need to install a new version, it manages that whole risky process.
So how do you get these new updates onto your devices? Well, you could go visit every single one and plug it in, which is just not going to happen. Or you do it the smart way, with over-the-air updates, or OTA. This is the magic that lets you send new firmware over Wi-Fi or Bluetooth from the comfort of your chair. Honestly, for any modern connected product, OTA isn't a luxury, it's a necessity.
But wait, what happens if the power cuts out or the network drops right in the middle of an update? You could end up with a bricked device, a very expensive paperweight. And that is why this quote is absolutely crucial. A rollback plan is your safety net. The pro way to do this is to have two separate memory banks. The new update gets downloaded to the backup bank. Only when it's 100% verified does the bootloader flip the switch. If anything goes wrong, no big deal. It just reboots from the old working version. Crisis averted. Now, as soon as your device is connected to a network and can be updated, you've opened a new door, a door for attackers. So the next critical question is security. How do you stop somebody from cloning your device, or worse, uploading their own malicious code?
Your first and most powerful line of defense here is Secure Boot. It's basically a digital lock and key. Before you send out your firmware, you sign it with a secret, private key. The device only has the public key, and its bootloader will flat out refuse to run any code that doesn't have a valid signature. This slams the door shut on unauthorized firmware. And of course, every platform handles this a little differently. The Pi leverages all the powerful, mature security tools from the Linux world. The ESP32 goes for a hardware-first approach, with things like Secure Boot literally burned into the silicon with eFuses. And the STM32 gives you the raw tools, like memory protection, so you can build your own custom security solution.
Phew, we've just walked through a lot of steps. Imagine having to do
every single one of those things manually every time you change one line of code. It would be slow, painful, and you'd make mistakes. That is why the pros automate everything.
The industry term for this is CI/CD, which stands for continuous integration and continuous deployment. But forget the jargon. Just think of it like this. It's a robot that watches your code. The second you make a change, the robot grabs it, builds it, runs a whole suite of tests, and if it passes every single one, it packages it up for deployment, automatically, every single time.
So here's what that flow looks like. You, the developer, just push your code to a repository like Git. That one action triggers a whole chain reaction. A server somewhere automatically starts building the firmware. It runs all your automated tests. If everything looks good, it packages the final binary and can even push it straight to your OTA server, ready for the world.
And the benefits of doing this are just massive. You move so much faster. The quality of your code skyrockets because bugs are caught in minutes, not weeks later in the field. You get this amazing traceability, knowing exactly which line of code is running on which device. And maybe best of all, deployments become way less stressful because you know the whole process has been checked and double-checked by a machine.
This flow here really ties it all together into one beautiful picture. You can see the complete cycle. It starts with code, moves through the automated build and test pipeline, gets flashed onto hardware, and the whole thing just repeats. It's a continuous loop of improvement. So, if there's one thing you take away from all this, let it be this. Having brilliant code is only half the story. A truly robust, successful product isn't just built on great code, it's built on a great process. That repeatable, automated system is just as valuable as the firmware itself.
Which really just leaves one final question for you to think about. When it comes to your own projects, is your deployment process solid and repeatable, or have you just been getting lucky so far? Something to chew on. Thanks for watching.